There is a laboratory in Houston where graduate students fire electricity through garbage. Right now, food waste, plastic bottles, coal, rubber tyres, the electricity lasts 10 milliseconds. And when they say what comes out the other side, most people don't believe them. This video is about why they should. What comes out of that lab touches the infrastructure holding up civilization and the drinking water of 2 billion people, and almost nobody knows it exists. Because every road you have ever driven on will crack and fail. Every bridge was built with concrete that is already degrading. Every building in every city on Earth was constructed with a material whose production pumps 8% of the carbon dioxide going into the atmosphere every year. More than aviation, more than shipping, more than all the world's cars combined. We have known for decades that we need an alternative. Nobody expected the alternative to come from garbage. In 10 milliseconds. This is the story of two discoveries, one that changed what we thought was possible and one made by a graduate student who wasn't even looking for it. But before I show you what that laboratory found, you need to understand why the material it produces spent 15 years being called the most important discovery of the century, and then quietly disappeared into tennis rackets. Because that failure is the reason the discovery in Houston matters so much. It raises a question I want you to hold on to. If this material can do everything the science says it can, why isn't it in every road, every building, every city on Earth right now? By the end of this video, you'll know exactly why. Every time you drag a pencil across paper, you leave behind layers of graphite. Carbon atoms, arranged in flat sheets stacked on top of each other hundreds of thousands of layers deep. Graphene is one of those sheets. A single layer of carbon atoms, one atom tall, arranged in perfect hexagons. Here is why that matters. Carbon, depending on how its atoms are arranged, becomes completely different things. Arrange them in a three-dimensional lattice, you get diamond, the hardest natural substance on Earth. Arrange them in flat stacked layers, you get graphite. Soft enough to write with, pull one of those layers off until it is exactly one atom thick, and something happens that has no business happening. The resulting material is 200 times stronger than structural steel pound for pound. Not slightly stronger, 200 times. It does not shatter, it bends. Stretch it to 25% of its original length and it springs back without tearing. A square meter of it, enough to cover a dining table, weighs less than a milligram. It conducts electricity as well as copper. It is, by almost every measure, the most extraordinary material ever discovered. The question materials scientists spent most of the 20th century asking was not whether graphene existed. Theorists had predicted its properties since the 1940s. The question was whether it could be isolated in the physical world. The answer came from a roll of Scotch tape. Researchers who worked with graphite had a habit. To clean the surface of a graphite sample, they would press Scotch tape against it, peel off the top layer and throw the tape away. The residue on that tape contained thin graphite flakes. Nobody paid attention to the tape. It was waste. A postdoc in André Geim's lab at Manchester, a physicist named Oleg, noticed that by folding that tape and peeling it repeatedly, the layers could be separated further, then further, then further still. Within half an hour of picking up the tape, they had a device. Within a year, they had isolated a single layer. Geim put it simply. What those researchers had been throwing away for decades, they were throwing away the Nobel Prize along with the tape. Their paper appeared in Science in October 2004. In October 2010, Geim and Konstantin Novoselov received the Nobel Prize in Physics. Which raises a question worth asking: who was André Geim, and why did he find what everyone else had been throwing away? Geim ran his lab on a specific rule. Friday nights were for experiments nobody was funding. Low stakes, curiosity only, no pressure to succeed. Most of them went nowhere, but he understood something most scientists do not. The willingness to look foolish is the price of finding anything genuinely new. Graphene was a Friday night experiment. The tape was waste. The Nobel Prize was in the bin. And then the world decided change was going to change everything. Graphene would replace silicon in computer chips. It would make bulletproof armour light enough to wear comfortably. The European Union committed €1 billion to the Graphene flagship, a 10-year initiative to translate laboratory science into commercial products. Almost none of the promised applications materialised. Not because the properties were wrong, every measurement confirmed what theory predicted. Two things killed it, both mundane, neither mentioned in a single press release. The first was manufacturing. The Scotch tape approach produced graphene in quantities measured in micrograms. You cannot exfoliate your way to industrial scale. The industrial alternative involved growing graphene atom by atom on a metal surface in a furnace at over 1,000 degrees Celsius. That produced larger sheets but required a transfer process that damaged the graphene and introduced defects. The commercial price of the output ran between $67,000 and $200,000 per tonne. Steel costs $700. At that price, adding graphene to concrete was mathematically absurd. But here is what nobody anticipated. Some researchers did solve the manufacturing problem. They got the price down, mixed graphene into cement, and ran into something completely different. The second killer, the one nobody talked about, graphene sheets attract each other at the molecular level. Van der Waals forces, the same forces that let geckos climb glass, pull the layers together. In a cement or polymer matrix, instead of dispersing individually and reinforcing the composite, the sheets stuck to each other and formed aggregates. Lumps of graphene, useless, inert bundles sitting inside the material like knots in wood. Researchers tried every solution available: surfactants, sonication, chemical functionalization. Some worked partially in the laboratory, none worked at industrial scale. By 2019, 15 years after the Nobel Prize-winning discovery, graphene was in tennis rackets and premium bicycle frames, not in concrete, not in roads, not in the materials that determined whether the construction industry could have a low-carbon future. 2 killers, 15 years, no solution on the horizon. And then a doctoral student in Houston read a paper about something else entirely and applied it to carbon. Dui Long grew up in Vietnam at a time when a career in serious science meant leaving. The equipment and funding weren't there. To do the kind of work that mattered, you had to go somewhere it was already happening. He arrived at Rice University on a fellowship. No publications yet, no reputation. A scientist with everything still to prove. What he found at Rice was James Tour's lab, built on a specific philosophy. When a student made a discovery, the student owned it, not the university, not the lab, the student. The goal wasn't just papers, it was scientists who could take what they found and turn it into something that existed in the world. Luong had been reading a paper about flash Joule heating, firing a pulse of electricity through a material to create phase-changing nanoparticles of metals. The paper was about metals, not carbon, but he thought it might be interesting to try with carbon. Not graphene, just carbon. He wanted to see what happened. He built a small reactor. He filled it with carbon black, the same black powder used in tires, in ink, in 100 industrial processes. He connected the electrodes. He discharged the capacitor. The flash lasted 10 milliseconds, a bright, instantaneous burst of light that lit up the reactor and vanished. Luong described it later with the understatement of someone who still hadn't processed what he'd seen. He said, "I did not expect to find graphene." He ran the characterization. Then he ran it again. Then he went to get his advisor. Tour looked at the data. Then he looked at Luong. Neither of them said anything for a moment. It was graphene, but not the perfectly ordered graphene of textbooks, where each layer sits directly on top of the one below in a precise crystallographic arrangement. What Luong had produced was something slightly different. That slight difference killed both killers at once. Here's what I mean. Perfectly ordered graphene layers attract each other. The Van der Waals forces that had destroyed graphene composites for 15 years acted on perfectly stacked graphene like a magnet. What Luong had produced was turbostratic graphene. layers misaligned at slight angles to each other, like a deck of cards dropped on a table rather than stacked perfectly. Turbostratic layers interact weakly, they slide apart. When mixed into cement or asphalt, they disperse individually, each sheet spreading through the matrix, bonding to the surrounding material, reinforcing the composite at the molecular level. The clumping problem was gone. Luong had not designed this, he had not set out to solve the clumping problem, he had not even known it was the problem he needed to solve. The specific temperature and duration of the flash, carbon heated to 3000 Kelvin and then stopped, produced turbostratic graphene instead of the ordered variety. Not because anyone planned it, because that is what the physics does at that temperature. One accidental 10 millisecond pulse. The manufacturing cost collapsed because the process used electricity and garbage instead of precision furnaces. The clumping problem dissolved because the specific disorder of flash graphene made it physically incapable of aggregating the same way. The paper appeared in Nature in January 2020. Not a specialist journal, but one of the most prestigious scientific publications in the world, reserved for research of immediate importance to science broadly. Luong founded a company to commercialize what he had found. He called it Universal Matter. In keeping with the philosophy Tor had built his lab around, Luong left Rice and ran it himself. As of 2024, Universal Matter has active partnerships on 4 continents, laying roads, testing concrete mixes, and scaling the same accidental process that started with a handful of carbon black and a capacitor. Universal Matter recently worked with Tarmac to lay the world's first public graphene-enhanced asphalt road in Middlesbrough, England. Not a test track. A public road carrying real traffic in real weather. A 5-year European Union-funded field test on a heavily trafficked road in Rome confirmed that graphene-modified asphalt, using graphene as a composite additive, showed significantly higher stiffness, better fatigue behaviour, and greater deformation resistance after 5 years of real traffic. The Department of Energy's National Energy Technology Laboratory concluded from its partnership with Rice University that adding just 1% graphene to asphalt can triple the lifetime of a road. Triple, in controlled studies and early field tests. A road that currently lasts 15 years might last 45. The resurfacing cycles, the energy, the materials, the carbon, the traffic disruption, all happen once instead of 3 times. There are 60 million kilometers of paved road on Earth. The United States alone spends over $100 billion annually just maintaining them. Roads that last 3 times longer do not get resurfaced twice. That entire cycle simply does not happen, and the feedstock is whatever carbon waste was already being thrown away. Tyres from junkyards, coal ash from power plants, plastic that did not make it into the recycling stream, garbage in, stronger roads out, but roads are not the real problem. Here is something most people believe without ever questioning it. Concrete is permanent. It is not. It degrades, it cracks, it carbonates from the surface inward, compromising the steel reinforcement inside and ultimately causing structural failure. The bridges, dams and buildings constructed in the mid-20th century infrastructure boom are reaching the end of their designed lifespans right now, simultaneously, across the developed world. 42% of bridges in the United States are over 50 years old. In 2021, a condominium tower in Surfside, Florida, collapsed without warning. 98 people died. The investigation found decades of concrete degradation that inspections had flagged and deferred. The Colosseum has stood for 2,000 years. The concrete holding up the bridge you crossed this morning was designed to last 50 years. The reason for that gap is not engineering failure, it is chemistry. Roman concrete used volcanic ash that becomes stronger over time. Modern Portland cement concrete does the opposite. It begins degrading the moment it sets. The rebar rusts, the rust expands, the concrete cracks. The cracks let in water and carbon dioxide. The process accelerates. 4 billion tons of concrete are produced every year. Every road, bridge, dam, hospital, school and apartment tower. The modern world is made of it. And at the centre of concrete is cement made by heating limestone to 1450 degrees Celsius in kilns that run continuously on every continent, around the clock. Here is what almost nobody understands about cement production. You cannot fully decarbonize it, not with any technology that currently exists. Think about what that means for a moment. Every solar panel, every wind turbine, every climate pledge from every government on Earth, none of it touches this problem because the carbon does not come from the energy source. It comes from the chemistry itself. When you heat calcium carbonate, it breaks apart chemically. Calcium oxide remains, carbon dioxide is released, a direct, unavoidable product of the reaction. You can run the kilns on renewable electricity, the carbon still comes out. The result, cement production alone is responsible for approximately 8% of global carbon dioxide emissions. The same figure you heard at the top of this video, and it bears repeating here because now you know why no energy transition touches it. The only path that works is using less cement. Adding just 0.1% of flash graphene to cement, 1 gram per kilogram, improves concrete's compressive strength by 30% or more in lab and early trials, according to multiple Rice University studies published since 2020. Think of it as molecular rebar. Pure graphene is 200 times stronger than steel, but we are not building bridges out of pure graphene. We are dispersing vanishingly small amounts of it through the concrete matrix, where each sheet bonds to the surrounding material and reinforces it at the molecular level. The result is not 200 times stronger concrete. It is concrete that is 30% stronger, which at the scale of global cement production is the number that actually matters. 30% stronger means you need less of it to do the same job. Less concrete means less cement. Less cement means fewer kilns running. Fewer kilns running means less of the carbon dioxide that no engineering advance can remove from the process. And the degradation problem? Graphene reinforced concrete does not just start stronger. Early research suggests it stays stronger longer. The graphene sheets dispersed through the matrix appear to interrupt the crack propagation that causes conventional concrete to fail. A bridge built with it may not just be stronger on day 1, it may still be stronger on day 10,000, longer, from 1 gram of graphene per kilogram of cement made from garbage, in 10 milliseconds. James Tour has calculated that if all the cement produced globally were reinforced this way, the reduction in concrete manufacture would be the carbon equivalent of stopping the annual emissions of Brazil. The entire country of Brazil. Every car, every factory, every power plant, every flight. It is a projection, but it is grounded in peer-reviewed measurements of how much less concrete a 30% strength gain requires. And yet it is not being used at scale anywhere on Earth. And then there is a third application, quieter than the other two, but not smaller. Over 2 billion people on Earth lack reliable access to clean drinking water, not filtered or pleasant tasting. Clean in the sense of not killing them. The solutions that exist, desalination plants and municipal treatment infrastructure, require enormous capital investment and the kind of supply chains that exist in wealthy countries and almost nowhere else. 2. A graphene membrane works differently. Graphene is impermeable to almost everything except water molecules. When you create a sheet of graphene with precisely sized pores, gaps just large enough to let water through, but too small for salt ions, heavy metals or pathogens, you have a filter of extraordinary efficiency. Water passes, contaminants do not. The energy cost of pushing water through a graphene membrane is a fraction of what conventional reverse osmosis desalination requires. The membrane itself can be fabricated from local waste carbon, the same process, the same 10 milliseconds, without a precision manufacturing facility or an imported supply chain. A unit small enough to be deployed in a village, powered by a solar panel, producing clean water from whatever contaminated source is nearby. Fraction. The research is established, field deployment at scale is still ahead, but this application reaches people that roads and concrete never will reach. The 2 billion without safe water are not in cities where building codes get updated and construction firms run materials trials. They are in places where the barrier is not regulatory. It is access. And a technology that runs on garbage and sunlight clears that barrier in a way that nothing before it has. So why aren't any of these everywhere? The answer is not the science. The answer is 3 barriers. The first one, the one that actually controls the timeline, has nothing to do with the science. Building codes do not speak Graphene. There are no formal standards for graphene reinforced concrete in any major jurisdiction on Earth. An engineer who wants to use it today faces a chain that runs like this. The code does not recognise it, so the insurer will not cover it, so the contractor will not risk it. So the default is ordinary Portland cement concrete. Every single time, regardless of what the science shows. To understand why this matters, you need to understand how building codes actually get written. They are not written by scientists, they are written by committees, representatives from industry, government and professional engineering bodies, who review evidence, debate edge cases, and eventually reach consensus. The process is supposed to be slow. Buildings fall when materials fail. Cross-laminated timber engineered wood strong enough to build multi-story structures was invented in the early 1990s. It took 20 years to appear in major building codes. During those 20 years, engineers who knew it worked could not use it. The code had not caught up, the insurance did not exist. Graphene is entering that same timeline now. The Nature paper appeared in 2020. If the pattern holds, we are looking at the late 2030s before graphene reinforced concrete is a standard specification in major markets. Nearly 2 decades of cement kilns running at full capacity while the committees deliberate. The buildings going up right now in Jakarta and Lagos and Dhaka and Chongqing, the cities absorbing billions of people over the next 3 decades, will be built with ordinary concrete at ordinary carbon cost. Because the code is not caught up yet, the infrastructure going into the ground today will still be there in 2080. Its carbon is already spent. This is not obstruction. The bar for trust in critical infrastructure is high, but the climate does not operate on a committee timeline. The system was not designed to price the cost of waiting. That cost is real. The second barrier is price. Flash graphene is dramatically cheaper than what came before, but not yet at cost parity at the largest scales. Every month of increased production pushes it lower. The trajectory is clear, the destination is not there yet. The third is consistency. Quality varies with feedstock and reactor parameters, and industrial buyers have long memories. Several large construction firms tested earlier graphene products, got inconsistent results, and walked away from the category entirely. Convincing them back requires a paper trail of reproducible performance long enough to outlast their skepticism. That record is being built. Dui Luong did not plan to discover flash graphene. Andre Geim did not plan to discover graphene. Both came from the same impulse, curiosity about what would happen if you tried something that was not in anyone's plan. What came out of that Houston laboratory is 1 process and 3 outputs. Stronger concrete from 1 gram of graphene per kilogram of cement, longer roads from 1% graphene in asphalt, clean water for 2 billion people, filtered through membranes made from garbage. All of it from the waste the world is already producing. All of it in 10 milliseconds. The technology exists, the data is promising. The barriers are real, but they are the kind of barriers that move. Prices fall with scale. Consistency improves with production volume. Building codes change slowly, but they change. Cross-laminated timber made it. This will too. The question is not whether flash graphene gets adopted. It is how long the gap is between what the science shows and what gets built into the ground. Every year that gap stays open, ordinary concrete goes in instead. The carbon gets spent. The infrastructure locks in. Ask your city council why they're not specifying flash graphene asphalt. Most of them have never been asked. That question has an answer. Getting it is how the gap closes.